No problem.
But no, I will start with my. Here, this was where I get it from the lecture. So. I called my model the metric universe. At first, it was the shape of the universe, but there were 5 versions in Vixra, and they limited updates to 5, and I could not write another
update.
And I have to do to use a new name because there are some new ideas with the metric or system. I called it now the metric universe. So
very good. That's interesting.
So
Gerd, are you from Germany yourself?
What?
Do you live in Germany? Are you from Germany or?
Yeah, I'm from Germany.
So similar, Christian, you're also from Germany. Do you live close by or?
Yeah, native Munich.
There is also a German version of the same of the model. You can download it. I wrote all in English and in German.
Yeah, thanks. It's good for understanding sometimes in different languages, but I think the English version will just do. It's just fine.
Here, Professor Lanzos is a Hungarian name. That's why it's called Lanzos. Yes, told in his lecture that the metric wave field should have it's a 4-leg electromagnetic field with some which has some vortices, and these are arranged in a cubic phase center crystal lattice. That means the universe is quantized, yes, and that's a picture of a cubic phase centered crystal lattice here. As you see, there are altogether 4 of these points in a cube, and this side should be the same as the Planck's smallest increment. Yes.
The Planck length, yeah. The Planck
length. The Planck length.
Right.
Yeah. And I want to introduce a model which is based on the Planck's smallest increment or Planck length, and with Planck units, using Planck units. But because this model should also be the reason for the relativistic effects, there is I have to use the light speed as the greatest speed, and so I had to. The first step was to find a model which no, this is the coupling and so on. Here, as you see, the Planck's no.
Charge?
Yeah, Planck's charge and the magnetic field, as you see, and the altogether maximum speed is c. Yes. So, and I found some basics. The Planck's charge. I took Hall capacitor, and as you see, in order to get all with these size, and here are, you see, two the distance between two of these. I called them magic line elements. It's the same as here, but without rotation. Yes, and Lanzhou told that a rotation should be connected with electromagnetic field and distortion or expansion or compression with the gravitational field. So let's go on. I wrote some definitions, and at first I defined a capacitor, capacity with with the value epsilon r. Yes, and for the inductivity, I made the inductivity of one term is according to this but if you have
we know what you mean. You have the capacitive model, and you have also here the inductance.
Yes.
Of the unit system. Okay.
Yes.
So you're doing just fine. You just calm down. We have all this problem with when we first present. You are doing just fine. Carry on, please. Thank you.
Thank you also. Here are the transmitting of signals, and this you see in the mid there is no connection. It's from always from one to the overnächste, übernächste, was heißt das?
Just from we get you.
Yeah. And here I calculated the magnetic field strength, and you see for different, but the main idea is the inductivity is mu zero r0, and so we come to some definitions, energy and so on, and the gravitational force, and there are a lot of models which are based on the hydrogen atom, but there is the difference between electromagnetic force and gravitational force about 10 to the power of 40. Yes, but in this region I have this 1-to-1. Both forces are the same and cancel each other. Here are the definitions of Planck's elementary expressions, and I come here to the known thing that there is a frequency defined, and is speed of light, the quotient of speed of light, and Planck's elementary length. So you know that that's not new, but the model turns out the following expression. That's maybe not known for each, but
Gerd, sorry, but I have a small 30-inch screen on it. Can you a bit enlarge? Because I have a difficulty to see the equations. Can you enlarge the presentation to zoom some kind to make it larger? Because my screen is very small. It's only, my laptop is only a 13-inch laptop.
Yep, thank you. It's better
so,
now.
yeah,
that's much better. Thank you. Thank you.
So I can define an oscillatory circuit and calculate, and there is then it is oscillating with the frequency omega. Here, omega 0, I know it then, and that means I got a different. It's not a circle. The track is only the effective value. The real track shows like this, and this is like the Hertzian dipoles. Have the same shape, and it is, plays a role also in wave propagation, as we see later on. So here is you see, as you see. At the one end, you have a positive charge. At the other end, a negative charge, and it is rotating. And there is also a magnetic field, and that can be take on each value according to the magnetic and electric field. As in the as by Hertz said. But there is only, we have only a static model, but it's, in reality we have an expanding model, and to make this model expanding, we have to introduce an additional value which is it's
we see that it's the
case
density,
zero,
the reciprocal of the density, K0. Okay.
Yeah, can you give us, please, a small explanation? I don't want to disturb you, but there was an equation showing a -7/4 factor in the geometry of the oscillator chain. Can you please enlighten us where that geometry comes from in the beginning? Because it leads to the values which you use then later in the presentation. It was right at the beginning when you showed us what the oscillatory device or entity defined. And it had higher up. It had an algebraic equation of -7/4, if I remember properly. And I cannot at the moment follow where that geometrically comes from your initial cell model.
This one or which?
No, it was with one of the first pages already. But we can discuss it later also. I don't want to disturb your flow. Just before you go to the cosmological model and go deeper into that.
Yeah, this one.
Higher up, it was in brackets.
Maybe we should left Gerd to finish his presentation, then we make questions. I propose, so he doesn't lose his flow.
It was equation 10, I think, just up there.
But the main idea to add expansion is to add a third Eigenschaft, was heißt das? Eigenschaft.
Christian, you could probably help with some of the translations as well.
A property, a third property
probably, yeah.
To the vacuum, or better, I called it subspace because it's not suitable as ether because of this very huge third property, the conductivity. Normally they think that the vacuum has no conductivity, and that's why I have to specify my propagation function for generic electromagnetic waves later on to solve this problem. Here I introduce such a thing, but if we make it in the normal way, then we can moment. Because of the definition of here omega and C and R0, we get a different speed of light, and it's wrong. That's why we have to change the model. In that case, that it's not different from C. Yes. Here we have an equivalent circuit with series resistor or with shunt resistor. Both we can calculate from one to another by this formula, and in the end we use this model, but it's normally it's the same like this. We get two time constants, once this and once this. we can define, and to identify T1, we can identify with the Hubble parameter. I say parameter and not a constant, because it's not constant. Yes, and the second is identical with omega 0. And so we are able to set up here. This is an interesting definition. So we can. The problem is we can define the conductivity, but to get the exact value is a problem. Because we don't know the exact value of the Hubble parameter. Here I wrote here this for this value, but it's not actual. Yes, but we will specify it later. So we can. We came later. We come to this definition and to this yeah, differential equation. We can so. But there is a problem. There is the solution is not known until now. But I found a solution by two ways. One is here specified here with this. So and the solution is with is the hypergeometric function 0f1 defined by this formula. And there are some special solutions concerning to the factors. It's at first it's a harmonic solution, but it does not apply, and we use the Bessel solution. Here we have one, and the solution also can be right in that manner. And here we see we have not the frequency is not defined as it's shifting with time. Yes, and that's the problem of this whole.
It has to do with the cosmological expansion.
Mm-hmm.
It's not fixed. It's accelerating. That is what you mean. Okay, thank you.
But instead of the Bessel solution, we take another way, because it's a differential equation of second order. There must be a second solution too, and this is defined by the Bessel y function. This we can write, and this, we go on like with similar to the harmonic solution, but we cannot use the E function. But there is the Hanke function can be used, and there is are two factors, and interesting is Hanke function contains also an imaginary part, like with the E function, and So we can write it in this manner, but it's the same like this, yes. So and yeah, you see, it has no frequency defined in the real sense, and the amount of Planck's quantity of action is not constant. That means Planck's quantity of action is a time function. Which is a problem because it has been defined as a fixed value by the Kobe, not Kobe, CoData, yes. That's we will see later. So now we will find some easier functions to better calculate. And as we see, that's correct, and that's Näherung. Näherung, what's that?
Approximation.
Approximation function. And the green line is the effective value of H bar, yes, or H bar. Yeah? And here is the same for smaller times. It is here 0 is the time of Big Bang, and here is the time increasing. The 2 kappa 0 and epsilon 0 is no, the time is a time T1. Jetzt because with oh no. Because the subspace has now 3 values. We can define a lot of fixed values. R1 is Planck's length, but immediately after Big Bang, mass, time, as you see, and so on. And these values have Vorteil. What is a Vorteil?
Advantage.
Yeah, has the advantage that they are fixed values, independent from time.
Lorentz invariant. Yeah, okay.
Invariance, yes. Yes. So now we have defined at first here. As you see, here is the particle horizon. The approximation can be used nearly in the whole universe with good yeah. So now we here we have a second way to solve the differential equation by the Laplace transformation. I took this at first, but I could not calculate it up to the end, but I used it to obtain the phase and amplitude response of the the line elements. But now I found also a solution the same like with the first way on the first way. So so we came to the Laplace transformed, and the solution we will find by the retransformation, and with Mathematica, I can now I can retransform it, and we get the same result as here, but yeah, as above. And now I'm able to calculate the other values we need later. And at this time, I found in former editions I had here was an error which has been corrected now. So here we have the transfer functions we need because generic electromagnetic waves should be
maybe just tell it in German, and maybe
should be
you can translate. Yeah, can help you maybe. Yeah.
Should be propagate as interferences of the metric wave field. And so we need the transfer functions across the metric wave field. And this are the some of these functions, the locus curve, then the Bode diagram, frequency response, and phase response. We will need it later. And the phase angle, cosinus phi, and of the expression, etc. So now we have the phase delay and the group delay, which we need also later. So, and the frequency response for the transfer to the adjacent line element. So we now we will set up the propagation function at first of the metric wave field, which is totally different to the the one of generic electromagnetic fields, because of the extremely high value of the conductivity of the subspace. But we start like with the normal. And so we no, this at first the standard. It's only to the comparison. Then of loss affected medium also to the comparison, and now for our new metric wave field. For the magnetic field, there are two or three different field strengths defined. At first, the flux, which is without irrespective of the Fläche area. And at this point, we get come into play. The frame of reference with R0. So now we calculate and so on and so on. And with the Hanke function, it's a little bit more complicated. But it's the same way like with generic electromagnetic waves. So here we get the complex wave propagation velocity and the field wave impedance we need later. It can also be calculated in this way, but in former editions, once I took this one and then this one because of the section with later where I calculate some values with great very accurate. It's better to only to use one of these, and I will take this or in this case in this form. But it's, in principle, it's the same, yes. So here's some other expressions for the same, and no, I wrote, I depicted it. The propagation velocity in a linear time scale, in a logarithmic time scale, and as you see, the metric wave field only around the point T1 has its maximum at the Q factor is the same as the phase angle of this function, but it is only at this model the case. And if I write a Q factor, in German it's die Güte des Schwingkreises, but in English it's the Q factor. And in this model, it's the same value as the phase angle of the temporal function. And as you see, the phase angle is the square root of this value, and if you have logarithmic scale, the x-axis is divided by 2 in one case. As you see, the time and this Q factor. Yes, and interesting is that the metric wave field propagates with its maximum velocity behind the what is this particle horizon, and it's only 0.851 and so on. But the whole universe should have a radius of CT, yes, and this contradiction will be solved later. And also interesting is that the later the smaller the propagation velocity of the metric wave field, and that means now in normal conditions it's nearly a standing wave, and only the rotations and from the electromagnetic waves and some expansions or contractions from the gravitational field take place. So, but this normal propagation function we cannot use. The propagation function seems to be like this, and for greater values of the phase angle, we can find approximations which we can calculate very well. And here we say we see that there is a phase jump at this point with Q with a Q factor of 1. So in greater distances, it looks like a linear function, but in the vicinity of the Big Bang or particle horizons, it looks like this. Oh, here's the locus curve of field wave impedance. There's a problem to calculate approximative solutions in the normal way, but because if we use the normal way, we get this, and this rest it doesn't work. But there's another possibility I used. Here are the values or the expressions, therefore. Now we can set up a propagation function for the metric wave field, which is very interesting because the farther away, the greater the expansion velocity, and that means if we go from the observer far from the observer, also the distance plays a role for the calculation. The propagation value, or and there is a problem because it's abhängig.
Depending.
Because it depends on the time and distance, and we must calculate out the time in this way. Yes, so we have only here for the phase. It's temporary, and here we have but it must only depend on the distance, and in this way we cannot calculate. So here is very so and. And here is a very we need this later to calculate the Hubble parameter for greater distances. And this is the phase rate, and as we see, it's the same like the inverse of Planck's of the Planck's length, as we defined at first in the beginning. So here we some values for the world radius and for two different values of the Hubble parameter. This the old the 55 and this is the latest one. Here some. I tried to calculate some as you see here, here is a change of sign defined, and yes, the best would be have the German version in parallel. That's the line element, yes, special line element, and it's the normal form, and if we put in our values, we get this, and it's these values are only effective in near the world radius, which is normally it's 1, but as you see, also Planck's the Planck's length also is a part of the line element. Interesting is I named this this expression as navigational gradient. Yes, it will occur later. So next we need for the propagation function for generic electromagnetic waves as overlaid waves, and the normal is the box equals 0, but it's not. In this case, we will have get a similar solution, but not the same. At first, I take one line element into a conduction, and I can apply the conduction rules, and I will get the following solution. There is also conductivity, but this conductivity here turns to 0 with increasing time. But that means there is additional damping, as we will see later. Here we have the same solutions. Here. It's as the solution of conduction, and the value of this effective conductivity is at this time has this value is very low. So we cannot a normal we cannot detect it in a normal lab, but it plays a role with greater distances. Here we no. That means we get this is the normal solution for the generic solution, but in this model we have also a damping factor alpha with this with this value. R is the world radius, but that means in greater distances there is an additional damping to the normal geometrical damping. Here are the values. And so we can set up the propagation function, which only this is new here. But that means this was the approximation solution, but there must be an additional upper frequency limit, and we will calculate it this way. Here we get 4 different solutions. Once for the photon, for the there must be a temporal photon, space, so a time-like photon, space-like photon, neutrino and anti-neutrino. Here's the cutoff frequency. We need it also later to calculate the shape of thermal radiation. Here's the cosmologic redshift. Once again, here's a simple table with which one can calculate another value of the Hubble-Parameter, but that's not the correct value. Here is the near field of the Hertzian dipole defined. So that's are the current values of the universal nature constants for the standard model. Now the next section is very interesting, because we want to calculate in what with which
Cosmological constant.
no.
Okay.
You have normally you have the expansion velocity with different distance, and as you see, the farther away the expansion takes place with more speed than with smaller distance.
Okay. It gets accelerated. Okay.
Mm-hmm. That's why we use this our navigational gradient and calculate the Planck's length has a different value at the observer. The farther away we go from the observer, the smaller this value become. And so we, if we want to calculate, because this value is from the time, von früher, also from yeah. And to calculate the expansion velocity, we have to calculate the integral about the whole function. And I did this here. At first, I calculate the wave count vector as function of distance because
Christopher, should we take a short break because we are now 1 hour within the presentation? So Gerd can also have a small pause. 5 minutes break.
Yeah, I've read your paper.
Mm-hmm.
You know, the one you're getting this lecture from, the matrix universe.
Mm-hmm.
But it would seem to me that the math could be made a lot simpler if you included feedback conditions. You know, such as with an operational amplifier.
Hello, I'm back.
As a filter. I don't know, just thought, you know. But then your RLC circuit would then be part of the feedback loop. But that's just a comment. I don't really know about that. But I have another question. You are. What do you think of Mach's principle?
What?
Mach's principle?
I don't know. I don't understand.
Ernst Mach. Gerd, John asking you about Ernst Mach, the Mach principle. I don't know if maybe you can find it in Wikipedia.
A Mac, a computer. What? No.
Mach.
Mach, the Mach principle.
Mach principle.
Ah, so. Yeah, the Mach principle comes later because moment, I had this is a mass, yes, and if you calculate the value, you come. I will name it Mach mass later. And there's also a Hubble mass, the minimum mass, which is now here, now the Mach principle is you can the value is about 10 to 52 kilograms. The Mach principle, but at this point, all complete. With greater distances, the gravitational constant or not constant plays not a role, because if was heißt Himmelskörper? Celestial body is in the free fall. It is not in Bewegung. It not moves with respect to the metric wave field. So the distance between two celestial bodies in greater distance only is a function of the wave function of the metric wave field between both bodies. And I want to calculate this, and that is the case constant wave count factor. And as you see, this is nowadays, and this is the Big Bang. And the greater the distance, the later is defined from on. And this is about as R is is twice CT, and it's nearly the whole world radius. And the problem is to calculate it because you will not find an explicit solution, only an implicit, and I calculated some functions for it, and yeah. Here's the Hubble-Parameter. As you see, as the observer, the Hubble-Parameter is 1 divided by 2 c. That's it's not. It's a radiation cosmos, and it's a world radius. The value is 3/4 divided by t, and it's a dust cosmos. And you see, that's here you have the speed between the observer and celestial body, and this. But there is no solution above. But here we come to the point. We have different speeds, and we have to and the world radius should be CT, but it does not match. But we find a solution with match, and this is this with these angles and speeds, and here we have the whole universe expansion velocity, and so we come to the world radius CT. Yes. So we have solved the problem. So now we have another problem because we have a 4-day and not a 3-day cosmos, and there is a problem calculating calculating entropy. At first, we calculate the entropy of an electromagnetic field is normally the logarithm of what is this? The free possible inner configurations, and if we have an electromagnetic field, it's depending on the wavelength and the wave count vector. Now we have, if we see our universe as a black hole, then we have to calculate the entropy with P. But the problem is, with small distances, is no problem to calculate it. But if we have greater distances, the 4D volume becomes smaller, and we have the electromagnetic wave will turn back to the observer, and so it comes to the case that some what is some free some line elements are counted more than once, and that's not correct, because entropy is a statistical value, and in statistics each part must not counted more than once. And I tried to find a solution to calculate the correct entropy. As you see here, it's the curve 3. if we approaching the world radius, the wave goes back to the observer, and such the number of free was hat er denn da oben? Das war hier. Free inner configurations will decrease again. I calculated the number of free inner configurations, and as you see, if you are if you exceed the world radius in this model, it's possible that time-like vectors have double length than space-like vectors. You will get a smaller value here.
But it seems to me that at this point, you're inserting a fine-tuning argument.
Mm-hmm.
That is to say, a control system argument.
Fine-tuning, there is no fine-tuning because all...
yes, I saw that in your paper. You said no fine-tuning, but here you are, what seems to me to be a fine-tuning argument. You're selecting.
No, because the total value is increasing with time. It's not constant, and there's no fine-tuning then. Here's entropy as a function of time, and the only result is that the total entropy of the whole universe is increasing again and again, and there is no heat death.
Wouldn't there be a heat death though if you have entropy increasing?
Then is with entropy increasing, there is no heat death.
Okay.
If entropy will get constant or nearly constant, then there is heat death. The increase is also because of the expansion of the whole universe. There comes more and more free inner configurations are added because of the expansion.
If the entropy increases, it becomes more disorder, right? Disorder increases.
Yes. What?
Disorder.
Disorder.
Entropy increasing. If entropy is increasing, the disorder will increase.
Yeah, this order will increase.
Yes.
Because there are more increasing of entropy is disorder, increase of disorder. Yes.
Yes.
Mm-hmm.
So you have more configuration, and you are saying that there'll be more disorder because of the more configuration.
Mm-hmm. But as you see, if you have a smaller section of the universe, the entropy will decrease because a lot of free configurations are scrolled out of this area. But in the case of constant wave count vector, entropy of the start length or distance will become constant, but of the whole universe it will increase. Because we have a wave which is which propagates at the top. Here yeah.
Can continue, please, with your presentation.
So now we have the temperature of the line element. So we haven't the Planck temperature because there is it's about a black hole. We have to no, subtract the
Angular momentum. Maybe. Do you mean angular momentum?
Mm-hmm. And so we come to a temperature of the of 0 Kelvin to the metric wave field, and not to this value. Here, why there is it may be that there is superconduction. There are normally Cooper pairs with a double value of with a double charge of an electron, and if we take this, we come in the vicinity of only 2% below the conducting band, and if we have a voltage, then there is no more resistance. But it's only an idea. Maybe that is a wrong idea. Yes. So now we calculated the value of Planck's quantity of actions, but it says no. It also depends on the distance, because the old values were greater than the actual ones. But it's just not the interesting part here. Now we come what happens in the first time immediately after Big Bang with energy, then we get some functions. Here the first, and here the second maximum and the first. And the length is the idea is the normal at the Big Bang, the universe get some energy, and a part of this energy is put in to establish the geometric wave field. There is a remainder then will be coupled in as cosmologic background radiation, and if there is yet another rest, it will be transformed into normal matter. So, and I made calculated the spectral function of the first function of the first maximum, and there we find it's a time. That means it's similar to a Q factor of half and second maximum. But now I have had the idea that to answer the question why the shape of the thermal radiation and also of the cosmologic background radiation similar to that of oscillating circuit with the Q factor in half. That's the function of power of this circuit, and that's the tuning. If we put in the values, we can calculate it, and now we want to calculate the cosmologic background radiation. Here are the normal expressions. And the incoupling is at a Q factor of half, at T1, and with this frequency. So and at first I tried to calculate that's the oscillating circuit with a Q factor of half as input frequency at the incoupling, and I calculated it with cosinus phi is only the real part of the function, and with the frequency response. And so I come to the that's the Planck's curve. So I think that it can be approximated, and that means the symmetric wave field has an upper frequency limit. I calculated it for Here you see before the metric wave field has been established completely. Both frequencies have the same value, and here is the incoupling. And then it will be split it into 4 line elements and some other transformations, and so we have at least another frequency and a different redshift. That's for the line element has this redshift, and overlaid frequencies have this. So it's a little problem to calculate the curve, but I found a way to calculate it. So here, at first we find Planck's curve for technical signals with with a Q factor of a half. So here, that's the input, and that should be output. That's Planck's rule, radiation rule. So we see the input, and it would be with a frequency, but that's integral where the values are multiplied and not added. But we can convert it into a normal integral because this function can be written as E function. So we set in our expressions we already calculated, and so on and so on. Then we must define function of the difference of both redshifts, and the main idea is not to calculate the redshift for both, but to let the input function at the same place, and to increase the upper frequency limit, what means the same in the result. So, and here's for the photon. We need the exact world radius at this time. Here's the formula to calculate. This difference function between both redshift functions. So that's a cumulative frequency response of a shifting upper frequency limit, and here are the difference to the between the output formula and the Planck's radiation rule. It's not so good, but we get a better solution if we made also so a group delay correction. That's the group delay. We apply it, and so we get, that's the formula to calculate the correct Planck's And that's the result. And as you see, it's nearly the same function, but we have to shift it at least. The correlation factor is correlation is this has this value, and as you see, that means if we can go out from a function from oscillating circuit with Q factor a half. That means the Planck's radiation, the cosmologic background radiation and all other thermal radiations has the same base at a Q factor of a half, and not at 3,000 years after Big Bang. Then it would be only a small needle, or yeah. Here's the Wien displacement. If you see such pictures, mostly they use a linear Darstellung, presentation, mostly with wavelength, and it does not see very well like a double logarithmic presentation is better. Then you can make a normal line, and here see you also why it has displacement law. In this other, this displacement is not a straight line. So here are the frequencies calculated, but that applies also to all other thermal radiations, because photons cannot be signed. It's they are timeless, and it is not known from which time they stem. Each photon is like another.
Excuse me, Gerd. We have a 2 hours limit in the presentation, so you have about 10 minutes more, a quarter to 10 minutes more.
Yeah.
To finish the presentation. So if you want to program the presentation flow, thank you.
Maybe another time, but here's the temperature. We can calculate this formula. It's extremely exact. Then how much how many line elements really fit into the universe at this time? As you see, here is only one, and there is a problem which have all other with their cosmologic background radiation. There is if you have the entropy is increasing and then decreasing. Here you see I have the same, but not at 3,000 years after a Big Bang, but it's the first time. But as you see, here are only 112 photons and it's a problem of statistics. Statistics needs a minimum number of free inner configurations, yes. And if the number is only one, you cannot calculate an entropy, yes. Well, here, let's you can more and more calculate here. Here, why we have more normal matter than antimatter? The problem is the matter is has their base here or at 3/4, and here we have the metric, and it works as a lens, and all values are we see all values through this lens, and because this lens is oscillating with frequency and the amplitude of h bar, we cannot focus properly, for example, an electron. That's a real reason for Planck's uncertainty principle, because the whole the whole metric wave field is oscillating. Then here, the energy of the and so on. The aperiodic borderline case. What would be if we have our subspace with epsilon 0, mu 0, and our new introduced kappa 0. What is if we would apply a normal a generic electromagnetic wave, it would be extinguished nearly immediately. And the aperiodic borderline case is exactly at Q factor of a half. And you can see that's the input of our universe is a Dirac impulse. It's an impulse with a square of 1 and infinite high. And yeah, you can calculate the spectral function and so on and so on. Here, photons. I made okay, have a new that there are 4 kinds of photons: time-like, for space-like photons, and so on. And the time-like photons and space-like photons behave immediately after Big Bang like neutrinos, and vice versa. Photons have this redshift, and neutrinos have a higher redshift than photons. Here you define a photon circle where some yeah. That's a minimum. The photons rest mass, because it's the minimum mass which exists in the universe because of the effect of the Mach mass in distance of world radius.
So this is the Mach mass. The previous question is the Mach mass. The Mach mass.
The Mach mass arises from this expression.
Yes. Okay. We see it. Yeah.
And defined also. There's also M2. It's later.
Gerd, you have 5 minutes more during the presentation, because now we have a 2 hours limit for each. Thank you.
Yeah, we'll stop here. Yes, maybe we can.
Very good.
Yes.
Later.
So, so thank you very much. Yeah.
Thank you.
Yes, thanks.
Excuse my English.
No problem. See, we can have a Q&A session next time. Maybe after, see, I think John is present. Christopher said next week it's not possible. So we may have on the 11th of March, and then John may be presenting that time. We'll see.
Great.
And after that, we can have a Q&A, probably 18th of March. We can
Yes.
have Q&A.
It's possible.
Possible.
Oh, great.
Yeah.
But here are coming yet a lot of interesting
Yes.
objects. Yes.
Yes.
Some questions?
Yes.
I have only one or two questions. I'm
Yes.
just interested because your name Gerd, you said it's German. So Pommerenke sounds like Russian or Hungarian. Are you Russian or Hungarian?
No, it's German.
It's fully German? Oh, okay.
Maybe Polish.
Polish. Okay. That makes sense. That makes sense. Okay. The other question is one more question, and then I will turn over. I think the main Q&A will be on the 18th. But one more question I have is that equation 260 seems to be quite interesting because it is from Einstein equation, and I think you are substituting for time with space. I think you are substituting all the time equation to space equation.
This where the sign
260. If I remember it correct, 200 equation 260. 260 is ds square something. Ds square in terms of the space. 260. 260. The way up.
260.
Yeah.
Here.
Yes.
Uh,
So you are in previous equation, you are replacing the time.
that it comes from here. I started here with and
Minkowski space, right? It's a
here is
Minkowski's.
minus, and then from the
Yeah, I get it. Yeah. Anyway, we will have more Q&A. That's fine.
But it depends on the both expressions. It's complex. You cannot say if it's plus or minus.
Okay, that's fine.
But normally these are, I think, will be 0 and with greater distances. But you can calculate. They are defined here anywhere. Here it's yes. It's the definition of the both A and B.
Okay.
Here you can use theta, I think, and theta is. Minus 1 and
oh, okay. Infinity. A starts at infinity, converges to -1. Is that the one? The factor half erases from 4th root, you see.
Here from yeah. You must see if you have former edition. I forgot this half and wrote it to another formula that I got the same result, but I redefined it here. So we can come to the factor 1 half. But you must pay attention here, yes? Only use the same as in the same edition.
Okay. So can there be faster than speed of light, superluminar? Is it possible?
Not really, but I had here where a little bit maybe, and later what's this? Ein bisschen weiter.
I think it must be equations 301 and 302, the time like and space like photons.
Yes. And there's another possibility later in the end, because all natural constants aren't constants, or most of them. It is possible that in the vicinity of black hole, noch weiter hinten. Nee. So, Tabelle, warte mal. Tabelle. Ach so. Here is the program. You can copy it, but not in the Firefox, but in a normal PDF viewer. You can copy the text. Tabelle. 227. I don't find it here.
Use Control F. Find function.
I don't find.
Anyway, okay, I think we got the meaning. So
I don't find it yet. No.
no
Okay,
problem.
we will
It's
have
late
it
at night.
more on Q&A. Right now, we can wrap it up if you want. If anybody else has questions,
But in the vicinity of a black hole, fast moving celestial body may be fortgeschleudert. Was heißt das?
Accelerated.
Away from this, because e.g., for example, the mass and the gravitational constant change with a higher speed. Yes.
Yeah. Okay. No. Okay. So, can I ask also a related question to follow up from Rajan? Can I ask my questions?
Which?
No, Gerd. I mean, hello. So I'm very impressed about the quantity and quality of the work, and now I understand why cosmology is more complicated than particle physics. Particle physics might be quantum physics, and quantum mechanics might be more wide, more strange, but cosmology is more complicated. That's definitely sure. It's too many parameters to play. So I really have to, because this is actually your life work. It's obvious. It's enormous work, and I'm amazed about your work. So I had to ask you two questions which are more related to my interest and also Rajan. So you in equations 301 and 302. You said that there must be exist a time-like and a space-like photon. Can you please explain more what you mean? What does this physical mean? Because it is my understanding that in a space-like time there is no notion of time. It's like continuous action at a distance. Is that correct, or what have you said about this?
The time-like photon is the normal photon.
Yes.
And a space-like photon is, I think, the Broglie wave.
Is it the imaginary mass photon?
Yes. Which is
but
which moves against its propagation.
So it's like a tachyon. It's like
no. It's turning around like a loop, or
oh, it's spinning. It's a spinning photon. It's a rotational photon.
Is it anyway connected with a dark photon?
Yes, time-like photons. No, not a dark. No.
Equations 301, 301, 301, and 302. I have noted it here. It's the equations we give for the photons. 301. Equation 301. No. Up, not down. I think you mentioned it later on the questions 500 something. The equations for the time-like and space-like photons.
But there's also a problem with the spin. If I add neutrinos, then there is a different spin. Yes.
Mhm.
But I think I see the neutrino from the side. Then the spin is double, or I think I don't know. This must be solved. This problem.
It depends from the observer. The measurement problem of quantum mechanics. The measurement depends from the observer. Yeah.
And I think the three different neutrinos are the same particle, and the neutrino oscillation comes from the following. They are fermions, yes, and a fermion must have a different energy than another fermion, but it
The
also
Hall exclusion. Yeah.
but it only applies in the electron shell of an atom. In vacuum, it does not play a role. But if the neutrinos pass the Earth's kernel, Erdkern, there is a very compressed matter, and there is the possibility that two neutrinos pass the same electron shell is greater than everywhere than in the vacuum. And so if two are the same neutrinos are in the electron shell, one must change its energy and change its kind.
Okay.
Mm.
That's all. So, and one question more I have. Papers. Page 63, equation 290. I have here. Page 63, 290. Yes. So, can you explain more? What all this? What is this? The light, the speed of light, c, and then you have the c underlined. This underline. What are these? I recognize the impedance. These are impedances, but what is the c underlined?
Yeah, this a complex value.
Oh, it's the imaginary part of the complex number. So it's
no, imaginary and real part, and
yes.
the imaginary part is then in this case is 0.
Okay.
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 And that's the exponent of the exponential function e to the power of gamma r. Yes. And,
yes. Okay.
And this is and that's the frequency response.
And the last question, Gerd, and you calculate a cutoff frequency. I'm not an expert in cosmology, in no way, but this cutoff frequency has something to do with the Planck frequency, the highest frequency, the highest radiation we can observe in our universe. Is that the same? The Planck
I did not understand anything. What?
Yes, you have calculated a cutoff frequency. I think it's cutoff. You know, you cut the frequency bandwidth. I think
calculated what?
Yeah, it's figure 21.
Frequency.
Figure 21. Figure 21 and 22.
Kappa 1? No.
Figure 20.
Cut off.
Cut off.
So upper cutoff
frequency. Yes.
Yeah. It's the cutoff frequency is not fixed has not a fixed value or better normally it has it, but I calculated in that manner that I increase the maximum cut-off frequency because both metric wave field and the overlaid wave have different redshifts, and so it's better not to have the upper cut-off frequency constant and redshift them differently, but to let them the metric wave field frequency and the overlaid frequency constant, because at the point of input it has had the same value, yes, and to increase the upper frequent, nee, was war, wie?
Limit?
Yeah, per
Yes.
cutoff frequency.
Yes, but maybe you didn't understand my question. I'm asking specifically about the blank. Christopher, can I share my screen?
Yeah, the upper frequency, no, limit, nee.
No, Christopher, hello. Can I share my
Hello.
screen? Can I share my screen so I can?
Yeah,
show
Gert would have to
my
stop sharing
question?
his.
Yes.
Or yeah, give it a go there. I think Gert would also. It would mean Gert would have to stop sharing his, obviously. But
Normally the upper wie heißt denn die?
It's blank frequency. Gerd, can you stop sharing your screen so I can show you what I mean? What I mean by blank frequency? The formula. I want to show you equation.
One moment.
You mean the Haber G over C to the power of 5, or under the roof?
The
Yes,
upper
exactly.
cutoff frequency
Yes.
is normally has normally the following value, because and it is fixed and it is
It's the highest observable radiation in the universe.
that's the upper cutoff frequency.
Yes,
You can
it
calculate.
is related with the Planck length. Yes.
It's according to the Abtas theorem. What is the Abtas theorem? A sampling theorem. It's normal. The sampling theorem means that it's the upper cutoff frequency.
Okay, so what is the value you have calculated in your model for the
the value? No, it's normal. You can calculate moment.
It's something tower 42 power of 10, 42 hertz, I think. Because I have it here.
I saw even a frequency of 10 to the power 100 or more.
Yes, because
Is it that 1.47466 to the power of 10 to the power of 104 hertz?
Yeah, something like that.
no, it's 42. It's 42.
So I can see that.
If you're interested in the values, you can look at table 10, and here you find it's the upper.
It's 2952 times 10 over 42 hertz. It's the Planck frequency, which has the
No, yeah, that's
that's
a Planck frequency at a Q factor of 1.
Okay.
Because this frequency and this frequency are changing, and this is fixed. Yes.
Okay. Because after the Planck, you get superluminous speeds. That's why.
That's the Planck. That's the Planck frequency here.
Yeah, but if you have calculated larger, but you say that you take also into account the expansion of the universe, so it's okay, because then if the universe expands, you get also a redshift of the wavelengths, so it's okay. You can have this
And you
kind
must
of
have a
calculation.
look. Just the Hubble parameter also can be calculated from it. If you divide it by the square
Yes,
of
okay,
the
okay.
Q factor.
Yeah, yeah, yeah. So I have no questions more. Thank you, Gerd. Thank you very much.
Mhm.
I don't have any questions anymore. If you want the other people here.
Yeah, if I may have one question I have about entropy. Entropy, you mentioned about entropy. So the beginning, before the Big Bang, you think there was a high entropy, high disorder, and then it changed to order? Is that
I think
possible?
it started with zero entropy.
Entropy zero?
Yeah, it's a Big Bang. It's zero.
Big Bang zero. Well, was it high before or low?
I cannot say.
So it increased after the Big Bang. It was zero, then it increased. That's what you are saying.
Yes, it increased, but as you see, I calculated the entropy of the as normally I calculated it started with zero, but if there is no free
Configuration.
yeah,
Configuration.
there's the problem of
N value, right? If n equal to 0, n equal to 1, then entropy is 0. K ln n, k logarithm of n. So n is 1, then the entropy is 0. So n has to be greater than 1.
No, greater than 1 moment.
N, the value of n, configuration, number of configuration.
Moment. Wo war das?
You have an equation for entropy, which is S equal to K times logarithm of n. Equation of entropy. Yeah, entropy.
Ja, Moment.
Page 80.
Was war das? Aha, Wien.
Page 80. Yeah, page 80 probably. Probably before that. Yeah.
I come here.
It's a big document, so it's difficult to
Yes.
Yeah.
to search.
It's a huge, it's like a book. Is it a book?
Yeah.
Oh.
Yeah,
I have not gone through this.
Actually, I was waiting for Gerd to hit the 1,000 mark equation.
No,
But now I see he has more than 1,000 equations. Gerd,
oh,
how many equations are there? How many equations? One.
I will find it. Moment. There was a function of how many line elements fit into the whole universe, and as you have seen below a Q factor of a half, there is only one.
Oh yes.
Yeah.
Can you explain this? I forgot this point. What do you mean only one? Only one what? I didn't get that.
Line elements. The line elements has
Photons.
the Planck length. Planck cubes. Moment.
Okay. So the foundation particle of the vacuum, it's only one. It must be one boson.
More,
So the vacuum consists of, if it consists from a subparticle, a hypothetical Planck-sized particle, it must be one.
I have found it here.
One type only. That's what you mean.
Yeah, here is it. Maximum of light elements n in the universe at the beginning. Here it's only one, and here is the metric wave field is completed, and up to this point, normally there is no fitting, but the whole universe is only one particle.
So it was a soup consisting only from one type of particle, say some kind of photon. There were no other particles formed. That's interesting.
Yeah, from an
with Regan, we wrote a paper together. We go through a paper with Regan. Actually, Regan did the whole work. My contribution was very small in this paper, and we say that the quanta of the if we say that space is a fabric, like Einstein said, and it consists from some kind of subparticle, there must be one type of particle only. It consists of, and probably it's bosonic type.
Because
there's no mass. But that's.
I calculated the correct world radius, which is not linear in this region, only in the approximation. And the Planck unit here is R1, yes, but as you see, there it's the world radius is greater than in the approximation until this, but yeah.
Yeah. Okay. So you mean what you mean by that? It's larger.
Yeah, but moment, but not moment complete. Here no, here nein, here cool. Moment, Weltradius.
You mentioned about that you have to change to p-value, which is the momentum, right? Instead of to calculate from metric universe.
Here's the exact world radius. You can see here's a half, and so it will.
So you mean the expansion of the universe? You mean the expansion? By larger, you mean the expansion of the accelerated expansion of the universe? Yeah. Okay.
And I calculated the value a sphere and
a torus.
A cube, yeah.
Cube. Okay.
Gerd, may I ask a question? Are you done so far, Emmanuel, with the question?
Yes, I'm finished. I don't know if
I jotted down during the presentation, which was very impressive to do a presentation from a book style paper with so many equations. I can understand how hard that is. I am also a Mathematica user, and I'm in the habit of always doing parallel calculations of the things I see while I see them. And if you may, I would like to show you what I calculated and have some questions from that. And for that to do, I would need to share my screen presentation so that you can easily grasp. I cannot verbally state that. So it's just a Mathematica paper, which has 4 questions actually, 2 simple ones, 2 not so simple ones. And we probably don't have the time, but for the simple ones we might have, and I'd like to show you your own equation, how that would look in iSpace mathematical framework. And I have some problems seeing in the result equations the geometrical structure of certain things. Maybe you have an explanation for that. Can I please share my screen?
Just
Gerd, you must stop sharing yours. Gerd, you have to stop sharing yours.
great. Thank you.
Yeah.
Thank you. So what I'm doing here is sharing this, and you should. Do you see my screen?
Yes.
Good. So let's make that full screen. I just jotted down the questions noted on recording of these text sessions for Gerd of the metric universe, and noted the equations here 1 to 5. And I can supply that afterwards for the other ones. But the most important thing, Gerd stated in the beginning, if I didn't misunderstand, that the Planck constant h would or could or should be a variable in some sense. And with these kind of things, when constants get variable, have really big issues. The statement poses multiple problems, and I cannot at all agree to. The reason why I can't agree to is 1a, I-space theory is able to calculate these constants of nature and doing that from a Lego style toy model. And that in its own makes Lego pieces not to be cuttable, bendable, or anything. But that would only be my argument, and we would be on par. If you're a different opinion, that's fine. But the next A1b is much more severe. And the von Klitzing constant, you have h over e squared, yeah. And the fine structure constant is nothing less than the mu0 times c. Can you read that, or should I make that bigger? Mu0 times c over 2 times e squared over h. And means the first part of the fine structure constant in the old definition.
Can you make it a bit
That's a good question. If I can make it bigger full screen, I cannot. I have to go out of the window.
Okay. So I have to adopt.
It's just tricky because I'm just sitting on the little
left.
Yeah,
I know. Okay.
But yeah, I can do that. Shouldn't be a problem. So when I do this here, I can grab that factor and go to 150. Then it's probably better. Yeah.
That's correct.
Yeah.
That's fine. Thank you.
So the mu0 times c over e squared over h is a standard equation for the fine structure constant, and until the redefinition of 2019 of the code data, which you also mentioned, where you said, it's a pity that they nailed that Planck constant. So I had in-depth 20 years thought over these kind of problems, and first of all, it's not at all a problem if they nail it. Because they gave free epsilon 0 and mu0. It's just a pity that they did that. But it is not a physical problem in any way, the way they did it. They did it very properly, and there is no problem with that as such. I really have to state that. The method is unusual, and it shouldn't have been done it this way, but it's not wrong either. It's just complicating matters a little bit more when you calculate these things. And I can prove that if you need. So the thing is, this here is constant for sure before 2019, because it is 2.792458 times 10 to the power of 7 over pi times 4 divided by 2, and is a constant by definition of human artifacts. That gives us the e squared over h as the von Klitzing constant, and I-space theory, but others also prove that this is the same value in all unit systems.
No,
necessarily is, and that means that if you have a varying running h, you get a charge change in square. I see no physical mechanism why that should be unnecessary and be valid. So that is the primary question I have, and I leave it to you to answer the questions in the order you want. You showed a factor in the beginning of something like didn't see the equation 4 over 7 or 7 over 4. I don't remember properly, with a minus sign.
7 over 4.
7 over 4?
Yeah.
Okay, thanks that you remember.
But can
I want give me a second. I wanted to see what that is, and then for the name, the metric universe, I didn't grasp why you named it metric. What is a metric lens? So that was not clear to me. It was an interesting concept with the rays over there, but what kind of physical aspect or mathematical aspect should make it a lens in this way? I couldn't understand. And the fourth is the most interesting one, probably for your own, as I have analyzed quickly your own equations here and found a factor of c to the power of 19 in effect. And let me show you that here. So first, confirm to me if this IK Pommerenke, which I had, is this the equation we talk about? So c to the power of 3 divided by mu0 divided by g divided by bar divided by the Hubble constant in frequency seconds. And that gives this numerical value if it is correct. And without ice-based theory, you can probably calculate it to the blue value and 10 to the power of 93 as a Siemens per 1/volt unit. Is that the one we talk about? That I did something wrong?
Moment.
I think this is related to the beginning of your presentations where you called it, of course, just with the
Yes.
I think I did it right.
Moment,
Christian has a very nice
36917.
framework which can very easily verify if theory is consistent.
Yes, that's the value, but I calculated a different value. Do you understand?
So you say, yeah, maybe then you have not used the Hubble constant in seconds, because in my unit system, it's only volt ampere meters in seconds, and the Hubble constant is a frequency. Meter per second per meter is a frequency. And if you insert the numerical value of 71.99 something in here, then you're doing something completely wrong.
Yeah. That's
Can I just apply that?
I calculated 1.369777 times 10 to the 93.
Yeah, then it's the same value, and you cannot calculate it more precise because you cannot measure the Hubble constant more precise in 2 to 3 digits, and it's not unexpected that you get a different value. The ice-based theory gives you an exact value from quantum constants for the Hubble constant and can predict the age of the universe to the nanosecond.
But that does not fit to the calculation of the Hubble constant using the electron mass.
It doesn't matter. The Hubble constant is what it is. If it is measured from 69 or 68 to 74, 72, 73, depending on the model, nobody knows better at the moment what it is. So this is all fine. Now, what is the interesting part? If you decode that, if you have the value that is in iSpace IQ units, that you don't know that, we skip that. That is the ITBH factor. And when I analyze that, you see that the SI time is to the power of 9 in your equation without you knowing. And when I divide that out from the power of time, we get that little nice equation here. Maybe I do it to 125, that we see it better horizontally. So your equation is an equal sign. Mathematica says true. I've done nothing wrong here. And what you can see, this here is just the number 299792458 to the power of 17. And when I analyze that and make it to the C, and I cannot make it to omega Planck, the Planck resistance would have in turn 10 to the power of 7 times 19 zeros, and I can't see that, so that is C for sure in this case. So it has the unit meters per second, so we need to compensate with second per meter to the power of 10 here with this value, and to the second per meter to the power of 5 with this value, and still got some second to the power of 2, which I cannot put to the other thing. So with all due respect, that doesn't look physical to me. So when you combine these kind of constants, you have to make sure that you get physical relations to all the constants to make use. I could show you in the Planck length how that, for example, works, and it goes off brilliantly when you do that with physical stuff. And
you are using the Hubble-Parameter value I calculated in my former
no, I have a theory for the Hubble constant. You can paper in SearchGate. This is my own equation. It is this H0.
And but the problem you showed above with the quotient of H and
let me show you what the problem with H is. So when you put the H of the Planck constant here as it is in the books, okay?
It was not a problem because the changes cancel out in this case.
Okay.
You say you have a varying H which cancels out, and hence you don't care, but then it doesn't matter if it would vary or not. Why would it vary then? Makes no sense.
Can you show me the first lines?
So that was your equation.
Here, stop.
Yeah.
No. A little bit back, higher.
It's just the beginning.
Stop. Yes. E e to the power of 2 divided by h.
Look, e squared over h we can show here. This is important for you if you don't have seen that. If I do e squared over h, I get but if I do that with I space value.
Yeah, but it doesn't change because
this is how an I space equation looks when it's physical. And when you put the numerical value of that simple thing, you get the von Klitzing constant immediately out of nothing.
So, Christian, let's get to.
But
it's a good feeling for equations when they get physical and when they are unphysical. Is all I'm saying.
No, I want to say because the definition of h as a fixed value makes no problem because the electron charge changes in the same manner. The quadrat.
No, it does not. It is also fixed. The mu zero and the epsilon change.
Yeah, there is no problem. No problem.
But if I don't understand the answer correctly. So
the best would be
says that there's a problem with your equations.
Maybe we discussed that in the section. It's too late now to go into the details. But I think, Gerd, you really have a look on I space theory on the constants, and as you have a Mathematica, this is super easy for you. You can insert the equations of constants of nature directly in your equation and see what they give geometrically. I mean, get that.
Yeah.
You just get a numeric value, but with I space theory, you can see your equations as I'm golden ratio to the power of 2 pi to the power of 10. That is geometry.
But I don't work with golden ratio. And where is
you don't work with golden ratio, but the universe does work with golden ratio.
No. Where is the frame of reference in your calculation? Because my
constants of nature are exact by design. They are not in a frame of reference. Had nothing to do with relativity. Constants are constants.
Sorry, Christian, because I don't understand the argument here. You both models, Christian's models and your models, are getting the same result, yes or no? Are you getting the same result from the calculation?
It doesn't matter if you put a constant from codata measurement into your equations by numerical value, if you put an exact value from I space with the same numerical value, just an exact one into your model. But
but the result is the same.
It shows you what you can do with it, and you learn from the equation what cancels. And why do you get the values you get? Not just numerically, but from geometry. This is a really big difference, amazingly big difference. You have to use I space as a tool to understand your own equations.
The best would be you send me your notebook.
Yeah, of course I can do that.
And you can copy my notebook from the PDF. You can export it as a text and import.
I know. I have seen a lot of your equations and read the cross-reading through it. I had not the time, unfortunately, to look for it. It was way too much to look into that. This is really impressive from cosmological point of thinking. But all I want to say is that I'm a really expert on constants of nature, and you should take the advice to say, go with your equations from cosmology, but insert the values of I space theory into your model, like a tool. And then you suddenly see results you would not believe. And
but I wrote that I'm not have the total exact results. I'm not.
You might get it.
I inserted the codata values from 2018.
Yeah, but I refrain to 12 or 8-digit precision when you can have infinite digit precision. What would make that sense? It makes no sense.
Yeah, I mean, okay, so there is no actually an argument. Both models are getting the same results, but not with the greatest accuracy that Christian proposed.
The Hubble constant is too imprecise to make predictions in curves. When you have a Hubble constant, you need the right Hubble constant. And with all due respect, I believe I have the right Hubble constant from quantum values. And quantum values are exact. And when the relationship from a Hubble constant means something, then it gives you an exact age of the universe, and that is 15.59 billion years exactly, not a second older.
Yeah, you have the other value I have had at first, but I calculated now another different value. Sorry.
If it's older than mine, it's probably wrong.
No, the older was the same as you had.
Interesting.
So you say it's more than 14 billion. They said it was 14 billion something before. So you say it's older than that universe, Christian?
Yeah, my universe, which is also your universe, is 5.9 billion years old.
But I have heard a different opinions from Christian interpretation of Catholic interpretation of the Bible. The universe is only 6,000 years old.
Wow. That's the order of magnitude. I mean, you're talking.
Which who will believe? I go with God. I go with God. I don't argue with God. Come on. But maybe
that's
6,000 years of his
email
years.
and wrap it up for you. This is late, and other
right?
people have surely other questions. And it was important for me that I did just in the background calculations, which could hint you to your own theory why it is doing the way it's doing it. I cannot understand how you conclude to this equation, because cosmology is a book with 7 magic things for me, and I will never understand it probably. So, but I do understand a part of quantum mechanics, and I do understand constants of nature probably more well than anyone else on the planet. And that means also something. And the quantum effects give you exact relations for everything by the nature of the quantum effects. There is nothing bendable, nothing which you can choose, or nothing is arbitrary. It's just exact as it is and will not change a bit. Constants are constant. They will not vary with time. Sure, not vary with time.
Yeah, I think that's interesting. You could apply the I-space values and put them in the equations to see if you get more exact results, Gerd. It could be a useful tool.
Just a tool. Yep.
Yes.
Yeah.
Yeah, you can benefit from Christian's research. Yeah.
Yeah, I think that's what he's
It's
suggesting.
it's very good framework for confirming a theory and finding exact values. Yeah.
But so Gerd, how would you summarize sort of the main point of your research? Would it be that the upper cutoff frequency is dependent on the size of the universe, which therefore determines entropy, or is there some other takeaway that we could get?
Yeah, the upper cutoff frequency is very easy to calculate. It's
Yeah.
I did the calculation here in I-space. Is it the cutoff frequency we talk about? 7.9501510. Oh no, it's the ratio. Sorry, the cutoff frequency of use of 1.47466 times to the power of 104 hertz, right?
No, I have 1.47039.
Yeah, okay, you've got 1.5, but we're talking about the same number. It's 1.5 to the power of 104, basically. Yeah.
Yes.
I also have an exact equation for that, and it has a geometric factor of golden ratio to the power of 5 times pi to the power of 9, if you're interested.
You know, I have a little bit different results than you.
Yeah, no, it's the same result, just with a different precision.
Yes, maybe.
A different result than me. It's just the same equation. I just put more
maybe
into those. That is all. You cannot play with cosmological values. It has only 2 to 3 digits of precision. I recently answered the ResearchGate question on that, and people don't get it. If you have only 2 to 3 values of precision in measurement of Hubble and have only 5 to 6 digits of precision in measurement of G, you gamble with theories. You make curves and fittings and that, but every 100th fit of every 100th ideas of millions of scientists, tell you what, just fit, because by chance. It doesn't matter. You have millions of people having ideas and everything fits. You cannot know. So you need a measurement with 9, 10, 12 digits, like Rydberg constant or G-2, that you don't fit accidentally. So when you have an equation, which some people have, like in the internet, like ResearchGate shows prominent people like Preston Gunn showing the G-2 to 14 digits without quantum electrodynamics, which is unbelievably impressive. But equally impressive is showing EG over H and Planck frequencies out of nothing in I-space theory. So you had a few geometric input values like 6961, golden ratio, pi, and a model, and you get all the constants of nature out of that. Do you think that is accidental? So you have precision in there, and that precision is just not clear how it relates to cosmology. When cosmology says we had a Big Bang, I'm not even sure there exists a Big Bang. Probably don't need a Big Bang. because the current telescope looking at the end of the universe sees galaxies where they shouldn't be. Are we sure about our models, or are we just guessing around? Models are cool, but models need scientific justification. And when the justification is we bend our constants, I'm not with you, not at all. We bend not constants. They are constant. They don't change.
Okay, interesting.
One of the things the recent paper I showed that actually what's happening is that if we use all the transforms, that actually it's a black box. It's like a black box. So we are looking at different perspective and we are trying to see a consistent result. So one model will see one way, another model will see another way. But maybe iSpace, I'm looking into the iSpace because you have a way of checking it out. So I give it,
it's a matter
the
of
positive
constraints,
result.
Rajan. There's nothing wrong or right with theories. You have constraints. And when you follow
Yes.
a theory of Einstein and theory of quantum electrodynamics, you get the shitty constraints of 14 digits G-2. And if your theory
Yes,
model
yes.
cannot explain it, it's probably incomplete. So iSpace is not wrong, but with that respect is incomplete because I have no value of
Yes.
calculating G-2 in a proper value yet. So,
Yeah.
there is
Yeah,
something
I'm
lacking
writing
in the
a
model.
paper. Yeah, I'm presently writing a paper about geometry of space and algorithm of time. I will be publishing along with Christopher, but I will have two more authors. Maybe Christian, you can. I talk about iSpace also there. We in a few months I will send that to you. Maybe you can check that and then you can be a co-author too. And then anybody else who want to be. But I think Manuel is there always because he's astrophysicist, and Christopher and myself are there. Then anybody else want to join, Gerd or Christian, you can join, and I will send that draft to you about iSpace because I talk about iSpace and it seems to be consistent, to what you are talking about. But I have no way of calculating it, so you may want to calculate and find out whether that is
Make a
consistent. So I
training
believe in
on how to calculate that. This is not so complicated. What is interesting
Yeah.
for you who have watched the last session where I presented my iSpace theory is that just yesterday, I was able to do a proof in iSpace IQ unit system where all the geometric values are not SI induced, but there is no human artifact. So we just have golden ratio pi 69611 over 6961 and nothing else, really. And I was able to prove that the Planck time in iSpace IQ unit system is just 1 over 6961 iSpace second, which is exactly what I wrote in the paper. I wanted to be the quantum of time, but I had no way intended that the quantum of time is indeed the Planck time quantum of time in iSpace IQ unit system. That knocked me off my socks. So I have with the quantum of time in iSpace IQ unit system, the true quantum of time is the Planck time. So then it's physical. That is physical. It changes everything. It's not just a model anymore.
Well,
And
that's
have a
very
Planck
impressive.
length, a quantized Planck length of golden ratio was 6961 squared iSpace meters. This is amazing. And I'm making now a table and preparing a paper for the end of May. There is a paper called Fractal Fract, and they accepted already the idea of publishing there. And as the iSpace theory is by nature actually a fractal theory of a fractal space-time, that fit very well into that, and I will shuffle them the constants of natures of iSpace IQ unit system under the hood of the fractal design geometry into that paper, and then we see.
If the time is physical, as you have proved now, does
Now,
it
I have
mean
mathematical proof. Mathematical proof is not experimental proof. It's just the proof that I
but
totally
you say
unexpected the time length in iSpace IQ units coincided with another equation which I found, and that is actually a very simple one. Is when you multiply Planck time times Planck length, then you get h bar over c squared, I think. Yes, or h bar over c, and that is.
yeah, but let me finish my question. If assuming that the time is now a physical thing, which is caused by some kind of energy, so time is now energy. Does it mean that it's not more prone to entropy? It's something different from entropy. It's I mean not different from entropy, but time is the source of entropy, not the other way around.
I don't
Because
think so.
say,
In the I-space model, you have this 10-dimensionality from space and subspace subdiversion, and this is the misunderstanding of the model. Would everything be Lego? It would have long ago been measured to be Lego in whatever precision or at least resonance frequencies of such Lego pieces, and it has not been to my knowledge. But with the Planck frequency of 1/6961, I have even experimental ideas on how to measure that as a resonance frequency in the lab. But what you see is inside the six-dimensional subspaces, everything is exact and has no entropy. It's exact. This is just is like a prick. Yeah. It's a speed of light moving, rotating prick, but nevertheless it's exact in its geometrical thing, like an Eiffel Tower maybe.
Yeah,
and you have a lot of these cells, and that is what is with Gerd's theory fully confirmed. You have an initial cell of size 1, whatever 1 is in your model, and this initial cells is Big Bang expanding and unfolds like a flower or whatever, or an Eiffel Tower or a geometric model to come to the curves which Gerd has shown. And I'm not a cosmologist, but these curves need to follow rules to create all the stars, the proper curves, the proper energies, to get rotational galaxy curves and all that what is necessary, including creation of planets and stars and a human being analyzing that.
Because
and,
they say
in this range, I think the entropy is there because entropy is about randomness and also about freedom of will. If you have not enough entropy, then you cannot even think on these problems because the little demon sitting on your shoulder would think for you. Stephen Wolfram has released a 250-page essay last week about where he bows in front of, and he never bows of anything. I really know him. So he bowed down to the ChatGPT demon and that what the hell is ChatGPT demon doing there? This is one of the most interesting reads I ever had when you want to go about consciousness.
Can you send it to me? Can you send it to me, please?
Have the time and have a look on that. It's in the internet, just in his blog standard. But this is 200 pages. You can read it in 2-3 hours if you're fast. And that is the thing ever written about. And he goes in detail to the entropy point there. And he's really an expert on that. I'm just a babysitter of entropy, but he is the expert on entropy.
Because a definition of entropy I have heard lately is the much more choices.
It's about computability. He calls it in his world computational irreducibility. I'm not even in the English word. So you cannot calculate it whatever computing power you have. It's uncalculatable by design. It's something like where probably even the quantum effects of Heisenberg come from, where say you either have the energy and the time, so the duality there with the inequality might be stemming from that inability to compute in the end. But that's supposed to have digital more like a holodeck than a physical entity. That is, of course, model-wise not debatable. But from what Stephen Wolfram is doing there, and they are the best physicists in the world, the best mathematicians in the world, and they are the best programmers in the world. And I-space theory wouldn't exist if he hadn't written Mathematica. And I'm really serious about that. Because with a pocket calculator, you don't do that. And I've talked to these people when I was there, and they are such precise people. This is near unbelievable. So my advice is have a look at that, learn from them, and see what they do there. And they are so advanced in that what they're doing. Even when ChatGPT, for example, is having some good marketing now today, as of being bought by Microsoft for $2 billion, is one thing. But what is ChatGPT is doing, they have done 20 years ago already in Wolfram Mathematica. 20 years ago, when nobody was talking about that.
So according to your opinion, is entropy the reason we have the notion of time, or is it the other way around? I mean,
entropy is the freedom of movement. For movement, you need time. If you have no time to move your cell, if you jump from time to time slot in Lego, or if you move continuously through a continuum, it doesn't matter as long as you arrive at your point, but you will not arrive by quantum jumps without time. I have seen
so
ResearchGate, which
time is more fundamental than entropy. That's what you mean. Time is more fundamental than entropy. Yeah? Is time more fundamental than entropy?
This is no. I'd say no. Entropy is not more fundamental than time. Time is the most fundamental thing, and the second most fundamental thing is length. and when you combine them, you get something, namely everything else, mass, charge, whatever. Yeah.
Okay.
And
yeah, very good. I will try to put in your values in my formula and see what if the results are better.
they will not be different. They will just, you get geometrical values, and this could be very interesting for you when you look on the geometry of the thing.
Yeah, but see here with your number moment. What is this?
Guys, I have to
cut,
go.
cut
I
off freak.
cannot stay more here in the institute. It's now 1 o'clock.
Yeah.
From the cutoff frequency,
Yeah.
I can exactly calculate my.
Thank you, Manuel.
Mhm,
We'll see you.
I must
Yeah.
leave. Sorry, but I'm
Thank you,
here.
Manuel. I have also
my
to
lab,
leave.
and
It's too late for me, and I need to go off tomorrow. So my cutoff time is in 2 minutes. Gerd, if you are interested, we are in German, so we can talk anytime to each other. We can even meet each other in Munich and have a session on that. That will be interesting. And so this is what I can offer if you want. And
Okay.
Thanks, Emmanuel.
Let us
Thanks,
know how what
Gerd,
come
thank you
after.
very much for your presentation.
Yeah.
Everyone,
Thank
guys,
you.
here.
Munich is not far away from Augsburg.
yeah, of course, that's why I'm saying.
So that's good. You can have a couple of beers, a
Yes,
lager.
exactly.
A Pilsner.
After the session, we might need it both.
Yeah. And
So
let us
thank
know
you guys
what's
very
going
much
on.
for this very
Keep us
nice
informed.
meeting. Gerd, tremendous work again.